Good morning. Good morning, everyone. Welcome to this DCMP student interaction talk. So today we have Dibya Sankar as our speaker. Dibya Sankar has did his BSc from Scottish Church College, Kolkata. Now and after that he joined in Department of Condensed Matter Physics and Material Science Department of TIFR in the uh, semiconductor physics in semiconductor physics using optical spectroscopy lab and he is working with Professor Sandeep Ghosh. Dibya is an IPhD student, joined as an IPhD student. So Dibya, now it's over to you.
Okay. Yeah. Thanks for the introduction. So I joined here in 2017 after my BSc. So now I'm in a about to finish. Final year, not about to finish. Today I will as I always do, I will just tell you the story behind building the setup of Magneto optical Kerr effect. Don't worry about these terms. I will explain one by one. The title of the talk, the curves in the title of the talk, you will see in a minute. But before that, as I always try to do, to say something like to convince that every day in science is something special, something interesting happened in that day. So if you find on Google, so in 1803, 3rd September is the day when John Dalton actually wrote in his diary. These symbols of elements, he drew that in the diary. So that is something remarkable in the context of science. That happened on 3rd September in 1803. Another interesting thing happened in 1752, that starting from 3rd September till 14th September, these 10 days never happened in the history of Britain in 1752, because they at that time they used to use Julian calendar, and that calendar was off by 11 days. 11 days corresponding to the solar cycle. So they shifted to Gregorian calendar, the current calendar, and that's why they shifted 11 days. So this from 3rd September to 14th September, this day never happened. But the interesting thing I found that people rioted in the streets thinking the government has stolen 11 days from their life. Anyway.
But the 3rd September, John Dalton was a British, no?
Yeah.
So when did he write this diary then? 3rd September did not happen.
No, that is 1803. That is,
that
is 100 years, almost 100 years.
Sorry about that.
Yeah. Okay. Yeah. So I always I like to start my talk with some comic. This is like I'm going to show you some all-nighter experiment and around the clock lab work. Some the result of that, and my guide may say that couldn't you work harder, and then I will say I will be dead by then, but I will have a PhD. So this is life. This is a PhD life. Anyway, finally the title of the talk. So you see these two curves now, the story behind transformation from this curve to that curve. So you see lots of things in this. One thing is, say, magnetic field. The B is magnetic field. So the magnetic field is different. So in the first curve, it is 1.53 Tesla. In the second curve, there are two curves. So one is 1.9, is another 1.2 Tesla. The temperature is different. That is 92 Kelvin, and another is 35 Kelvin. The signal to noise ratio is much improved in the later curve. And you see some distinct peak and deep in the later curve, but in the previous curve it was not very clear, but some hint is there. And more importantly, you see something in the inside of the second curve, which I will show you. I will explain you later, which is not in the first curve. So what is this curve about? I will explain that. So these, so in our lab, what kind of experiment we do? We do optical spectroscopy of 2D semiconductors. So don't worry, I will just explain, word by word, what does this mean. So these two slides are exactly copied from my previous journal club talk, just to give, some glimpse of what we actually do. So the optical word comes from optics, which means light. So it's ranging from ultraviolet to infrared. So we work in this range. So we have maybe a laser, which is a very specific frequency, but maybe a broad source where we have a band of spectrum. But we basically deal with light, some wavelength corresponding some energy. And the word spectroscopy is much more general, which means that the response over a large energy range. So you have heard talks on electron spectroscopy. People do in DNAP, they do mass spectroscopy. The word spectroscopy is very general. You want to understand some behavior, some response of some parameter over a long energy range. So we also do optical spectroscopy. Our tool is optics, photon. The next word is 2D, two-dimensional. It is basically atomically thin layered things, and they're actually, and two adjacent thin layer are actually attached through van der Waals attraction. So their in-plane bond is very strong, they're very stable, but the outer plane bond is very weak. So basically they're stacked, they're floating actually one top of each other. So in one word, if I want to say, it is just like graphene, but it's not exactly graphene, because graphene is just a sheet of carbon atom. But here we have, so these 2D semiconductors are some group of materials called transition metal dichalcogenates, where I will explain that later. But there you have a transition metal atom in between, and then there are two chalcogenide atom on, like one on top and one at the bottom. So these forms an unit cell, and this thing is atomical, like this thing is a 2D thing, and this and several such layers are stacked upon each other. So this is how these 2D semiconductors are formed. And now the word semiconductor, we all know. I hope you all know this. Sometimes it conducts, sometimes it's not. So it has some finite band gap. As soon as we excite some electron from the valence band to conduction band, they will start to conduct. And the materials we call semiconductors are those materials whose band gap is order of electron volt, which falls in the optical spectrum, the energy corresponding to the optical spectrum. So you can very easily excite electrons from valence band to conduction band, just shining some light on top of it. So light is actually a very good tool to study the band structure of this material around the band gap. So this is the optical spectroscopy of 2D material. I just wanted to just try to give you a glimpse, a sense like what we do in the lab. So we have something in the chat. Please mute me. Okay, post will do that. Okay, so what kind of experiments we do? So these are kind of a list of experiment setups we have in our lab, but my PhD is mostly concentrated on these three topics, though I'm now using other tools also like photoreflectance, luminescence, but my PhD work is related to like magnet, somehow is related to magnet. But today I will describe my setup, the magneto-optical Kerr effect setup, and what I have done using that setup. Okay, so as soon as you shine light on a semiconductor, this electron and hole are created, but they get, as soon as they create it, they get Coulomb bound. So it is like this, that you shine some light on a semiconductor, this electron and hole pair is generated, but they got Coulomb bound. So you will say like it's just like hydrogen atom, one positive charge, one negative charge is Coulomb bound, but this is happening in two-dimensional. So it's not like hydrogen atom in 3D, but they are confined in 2D plane. So this species is called exciton, the bound pair of electron and hole, and it behaves like a 2D hydrogen atom. So the bandage properties are mostly governed by exciton. Why? Because you see that this is a bound pair, so they have some binding energy. And so if you want to, if you shine light and try to reach the band gap, the excitons levels will come before that. Okay, so actually the bandage properties are mostly governed by this excitons actually, rather than the actual bandage. So as here you see, like even with light, if bandage is trying to do something, try to contribute something, but excitons levels are the main thing which dominates. So the optical properties of these materials are mostly dominated by the properties of the exciton. So now it's a good time to take a break, and if you think like कुछ समझ में नहीं आया but बहुत अच्छा लगा, then you can ask some question if you want. I will have several breaks like this throughout the talk. So
hello.
Yeah.
Can you repeat that exciton bandage thing? Bandage thing. I mean, I didn't understand that part.
Okay.
Exciton level part. I mean, this one, this figure.
Okay. So what I'm trying to say, this is the band gap. Okay, EG. Say. So, but as soon as this electron and hole pair are generated, they are Coulomb bound. This is a bound system. It has some binding energy. Say EB, binding energy. So, the exciton level will be the exciton energy, E exciton say, will be the band gap energy minus the binding energy of the exciton. So that's why these exciton levels you see, that is actually lesser than the actual band gap, which is less by the factor of the binding energy. So if you want to approach this level directly, so you want to get the information of this band gap, but before that you will phase this level rather than the the bandage exactly, but you will phase these exciton levels first. So that's why.
So that means we have a semiconductor which initially have electron and hole pairs, but band gap is defined when there were no holes. I mean,
band gap is defined. There is no exciton there. Then you can, and that is an ideal situation that will never happen actually. So every time.
So the question is, we created exciton or exciton were initially there?
So as soon as some electron are there in the conduction band and some hole in the valence band, you will find exciton. So in room temperature or any, unless it's absolute zero, at any temperature, there is some probability that some electron will be there in the conduction band. Okay. So excitons are always there in the semiconductors.
Okay, and the band gap is defined by taking the assumption that there is no electron hole pair.
Right. There is no exciton there.
Okay. Thank you.
So I just wanted to Vishwas and Ashish is there. So if I say something wrong, you can interrupt me and correct me.
Okay. So Dibya Sankar, one kind of naive question. So let's say I try to measure, following on Rishabh's question. So let's say I try to measure the band gap. Okay. Then what will I get? Will I get the energy difference between the valence band and the lowest exciton level, or I will get EG?
No. So if you just naively measure, try to measure the band gap, you'll always measure the fast exciton level. But there are ways to measure the band gap actually. So there are two levels. Say these exciton levels. This is like hydrogen atom, n equal to 1, n equal to 2 levels. But so if you know the energy of n equal to 1, the energy of n equal to 2, then you can using that formula of atomic energy, you can estimate the binding energy of what will be the binding energy if n equal to 2 n equal to 1 energy is Z1 and n equal to 2 energy is Z2, then what is the binding energy is this kind of hydrogen atom. Then as soon as you get the binding energy, you can add E1, the n equal to 1 energy state, plus EB, that will give you the band gap. Sorry, this is EG.
So there has to be some
that-
theoretical calculation input as well to get to the EG.
It's just a formula. It's
Okay.
not any theoretical calculation. It's yeah.
Okay.
And
Okay.
so
So-
I have just a single question. So
Yeah.
these kind of reduced band gap problems, I mean, these kind of problems appears in because of the presence of excitons, right? So these kind of, so as Shubhajit said, this band gap measurement problem, these problems can appear only in optical measurement problem, right? I mean, other than that, in doing transport or by doing something other measurements, the same problem will appear, or from there these exciton levels will not play any significant role?
direct it to Vishwas. Not sure much. Vishwas is there or not? I don't know.
Yeah, I'm here.
Yeah,
Actually, as long as you have a free electron, the excitons will always form. Yeah. So whether that's important, like in a transport measurement, the exciton is a neutral particle. It won't transport any charge. So if you are doing a transport measurement, exciton won't be important for you. But
So, okay.
No, but Vishwas, his question, I think, is, let's suppose if you have an electron gas, you don't have any free holes. So then what would happen? Then probably there won't be excitons.
then there won't be an exciton form.
Right? Because in transport, normally we are dealing with gases, either whole gas or an electron gas. We should keep on shifting the Fermi level. So the question is very apt. I mean, if you do, for example, STM, you keep on shifting the Fermi level by applying the bias, and then you hit the first the valence band, and then you hit the conduction band, and then you can get the band gap there. I'm sorry for jumping in, but Dibya asked me to do so, so now I'm taking the liberty. And in this
Sure.
diagram, which is there in front of you, this is a single particle picture. Meaning, if you put a single particle in the crystal, then you get these valence bands and this conduction band in the EK diagram. But many authors tend to put these exciton levels right there in this diagram, and it's not right mostly, because these exciton levels are you can say that the valence band is at 0 and then the exciton levels will be there. But in general, picking them parabolic and saying that in this diagram we can include exciton levels, it's not right, because exciton states are bound states and they have their own EK diagram. For example, the center of this EK diagram could be at let's say K point, such as in the case of 2D semiconductors in the single particle picture. But for exciton picture, the center of the EK diagram would be at gamma point, which will be 0 momentum point, right? So these things are different in that sense. And also, like when you shine photon and when you keep on increasing the energy of the photon, as soon as you go on hitting the exciton level, you directly create an exciton. So it's a quantum state which is directly created even before you actually create the electron hole pairs. At least this is what I understand after I talk to lots of theoreticians around, and also in the experiment. I mean,
Can you just repeat your last sentence? I mean, the last difference that you have.
Yeah. So let's suppose you are below, your photon is below in energy than the exciton, then the oneness state of the exciton, the ground state of the exciton. Then there will not be any absorption of this photon because there is nothing there. However, as soon as you hit the exciton energy, you see a sudden absorption, right? So that means that the photon directly created this exciton, and a free electron or a free hole was not even there. I mean, the free electron and a free hole will be created once you hit the actual band gap, EB. But it's just below that you directly create the exciton. So it's a quantum state whose dipole matrix element is just there. I mean, this state is directly created without even touching any free electrons or free holes. Just that way. Yeah.
Okay. Thank you.
So
yeah, I
Ashish,
should have said that this is a schematic. It's not actual. We try to understand these things like that, but we actually cannot put those excitons level just below the conduction band. It's a schematic. Yeah. Okay, then I will then go ahead. So now that there is, if we understand that there is some exciton, but how in our experiment, how we will model those exciton, the response of those excitons. So we can consider these as damped driven oscillator, because it's like electron and hole, they're bound through a Coulomb force, is bound through some spring. So you're trying to drive that with photon, but they eventually will be damped because of environment and defects and all these things. So we can model that as a damp driven oscillator, and for that we probably, I think you all know about this, something called Lorentz oscillator model. So it's basically for any damp driven oscillator, this is the frequency response of that. So if you see the real part of that, this function, it behaves like this. It's an asymmetric spectral feature. And the imaginary part of that is a symmetric peak. So we assume that this is the, sorry. So we assume, okay. So we assume that this is the contribution of exciton to the dielectric function. So they contribute it like this. So now ideally what should be that if you try to measure the absorption spectrum of some semiconductors, so before you hitting the actual band gap, there will be no absorption, but as soon as you hit the band gap, they start to absorb light, and how they will absorb light depends on the dimensionality and temperature and all these things. But if there are excitons, so even before the band gap, you will actually see these peaks. Those are actually the exciton levels. And in reflectivity, how that is reflected, so this is it's a reflectivity curve measured on my sample. So you see there are some overlapping of this feature, but that asymmetric spectral feature is there. So this is how the exciton reflectivity is reflected on the reflectivity spectrum.
What x-axis shows here?
Sorry?
X-axis is
It's
representing
energy. Sorry. Oh, I've named label. That is energy. Yeah.
Okay.
Okay. Then my work, as I told,
What scale of energy you use? I mean, it's EV or?
Sorry.
So what scale of energy that is in EV?
EV. Sorry, I forgot to. I mean.
So with energy, the reflection is changing.
It's basically the photon energy.
Yeah, photon energy.
Energy of the photon that.
So we are scanning with like this. We have something called monochromator. So we can select now I want 1.85 EV ka photon. So what is the reflectivity? Then I want 1.9 ka photon. What is the reflectivity? Like that we measure the spectroscopy. That is the thing I told. Like we want to. Yeah.
What is the photon being reflected off? Like the reflection.
From the sample. So my sample is there. The semiconductor is there. So the light is going like this and coming back. And this light has different kind of energy. So 1.8, 1.85, 1.9, I'm probing like this, and how much it's reflected, I'm measuring that. And that curve is what I don't know why it's not going back. Wait a second. How to do? Yeah. So for different energies, so here it is in electron volt. So I'm shining with 1.9 EV photon, and I'm getting 49% reflected. So 49% of those photon are reflected back. But then at say 1.98 energy, there is 39% reflectivity there.
Okay. And what explains that? Why does it depend on why is different energy photons reflect back with different reflectivity?
Yeah, that is exciton, right? So it will have, if you, as I told you here, So this is the response function of the exciton, right? So the real part of that corresponds to reflectivity, and the imaginary part of that corresponds to absorption. So so any damped-driven oscillator behaves like this. Even like a spring mass system, if you try to drive with different frequency, in the resonance, they will absorb the maximum energy, and in the out of resonance, they will not absorb energy, this kind of thing. And the real part of that behaves like, asymmetric curve like this, which is reflectivity basically.
Okay, thank you.
So Dibya Sankar, in that,
just one more thing.
Yeah.
Does this reflection depends on the angle, the angle of incidence?
Yeah, definitely. Yeah, it will depend. Yeah.
So these measurements are taken on which
on
angle?
0 degree or very small angle of incidence. So I'll show you two data. One was at 0 degree and one was a very small angle.
Oh, okay, thanks.
So probably Shubhajit was saying something.
Yeah.
So I was asking that in that next slide, next to next 14. So which peaks, like which peaks correspond to exciton levels here? Means how many exciton levels are we seeing here?
Yeah, so that is the question I try to answer. So broadly, you can see two transition. One is around say 1.92, another is at 2.14. So these two broad transition you see, but there is something in between here also, right? I don't know, it's not working now. So
in the middle there is
you see something. Yeah, something.
And in the left also, like let's say around 1.
So this thing.
Yeah,
this is something called interference. So when you have thinner samples, then these are layered materials. So what will happen that say some light goes like this, then after the first layer, some light will reflect back, and then from the second layer, sometimes light will reflect back. From the third layer, some light will reflect back. Eventually, the lower levels layers will not contribute, but few layers they will contribute, and these reflected light, they will interfere and they will give some interference pattern. So because of that, for thin samples, as soon as below bandgap energy, we see these things.
So how do you distinguish between which features are coming from exciton or interference? Maybe you will address later.
It's very I'll not address, so that's why I'm explaining here. So if you go, so I have cut here this energy, but if you go beyond that, you will continue to see something like this. So if you see something continuous like this, then it's obviously coming from the interference, not a feature.
So like if there is some excitonic level which is damped, like buried inside the interference region,
that happens.
Do some background subtraction or something.
Exactly. That those things happen. Yeah.
Okay.
For thinner and thinner sample, the interference pattern will come closer and closer. So eventually, as soon as the exciton ends, the interference starts. Now it may happen that exciton hasn't ended yet, but the interference has started. So these things have happened. Yeah. Okay. So my experiments are, as I told, is related to magnetic field. So what I do is what I try to measure is related to something called Zeeman splitting. We all know about Zeeman splitting. So for any spin degenerate energy state, if you put that under magnetic field, the degeneracy is lifted, and that state will split in two. So in my case, my valence band and conduction band, they are actually spin degenerate at zero magnetic field. But as so with right circularly and left circularly polarized light, you cannot actually distinguish between these two. I mean, so if you measure a spectrum with right circularly polarized light and you get a transition energy, the exciton energy, and then you repeat the measurement with left circularly polarized light, you will get exactly same curve, because they cannot distinguish. There is no, they are of same identical energy. But as soon as you apply magnetic field, there will be Zeeman splitting, and the splitting will be according to the Landé G factor of that energy state. And now if you shine say left circularly polarized light, it will address only this state, and with right circularly polarized light, it will address different state. Now there will be a difference in energy. So mathematically, for sigma plus polarized light, the energy, the exciton transition energy will be this. For left circularly polarized, it will be that. And if you somehow measure the difference between these two transition energies, you'll get this expression, and this is called the exciton Landé G factor. Okay, and so the thing is, if you somehow can measure this delta E, the difference between transition energies, then you will get exciton G factor in some way or the other. So in MOC, MOC is actually that technique to measure this delta E somehow, and from that we extract Landé G factor for exciton. So this slide is very, so I crumbled all the equations in one slide. So it's a very equation heavy slide. But how we extract Landé G factor from, so what is the using our theoretical model, how we extract Landé G factor, that I'm going to describe here. So we assume the Lorentz oscillator model for exciton contribution to dielectric function, and it's like that. Here, this E naught, yeah. So this E naught, this is the exciton transition energy. A is the oscillator strength, and gamma is the damping parameter, which actually gives rise to the width of the spectrum. And this thing is the background. So the exciton is there, but at the background, the material is there. So what is the material contribution to the dielectric function? And on top of that, we are artificially adding the Lorentz oscillator contribution for the exciton. So this is a complex number. So you can write them as in this form, epsilon1 plus I epsilon 2. And so once you get the dielectric function and these two parts, then you can get the N, the refractive index, and the K, extinction coefficient, using this expression. And using that, you can estimate the complex reflection coefficient. Again, that is a complex number. So you can represent that as A into e to the power I theta kind of way. And now you vary this transition energy, this delta, E naught by plus minus delta E by 2. So with plus delta E by 2, you get R plus, R tilde plus. With minus delta E by 2, you get R tilde minus. And using those, so once you get those two expressions from theta plus, theta minus, you get phi k, and for R plus, R minus, you get eta k. These are called MOC parameters. And from there, so you have artificially varied this delta E to get this phi and k, phi and eta. So now you know delta E. So sorry, this is okay. So now you know delta E, and now you plot this with magnetic field, and from the slope of the linear field, you'll get the Landé G factor. So this is how we estimate the exciton Landé G factor by measuring through MOC. And it's too equation heavy, and I was listening to some noise, so I think someone has some question.
So Deepoda, can you please explain the technique a little bit more, the MOK? So the Kerr effect generally refer to some non-linear processes.
Oh no, that is different Kerr effect. That is electric field induced refractive index change. That is different Kerr. The person is same, but the effect is different. I think this is called Kerr effect because Kerr first did this experiment. It's not related to the Kerr effect of optics. There is a second order electric field or something. So that is different. It's not that.
Okay, so in your experiment, there is no kind of electric field, kind of bias voltage, kind of.
No, nothing. Yeah, I just apply magnetic field on the sample and I measure the reflectivity, polarization sensitive reflectivity.
Right. Yeah. Okay. Thanks.
Yeah. Anything else? Okay, then I'm going ahead. So as Joydeep was asking how you actually measure it. So this is the optical setup. This is the old MOOC setup now, as I say. So let me explain you what's happening here. So this is something called monochromator. Okay, so this has the input light is a broadband white light, and then through a grating you actually get the diffraction pattern. So that is a rainbow. So you put a slit and some part of the rainbow, and you select one color. So this is monochrome. That's why it's called monochromator. So we get very precise energy photon through this. Okay. Then there is a polarizer at -45°, and there is something called photoelastic modulator. So this is a complicated device. So what it does basically, so there is the technique is very simple. So it has a fused silica, so normal glass. But I think you know that this glass are actually bifringent material. So what does it mean? That if you have a scale somewhere, so you'll see that if you so at the edge you will see some rainbow. Okay, so depending on the strain, the refractive index actually the refractive index of glass actually changes. Okay, and plastics also, the scales are plastic made, so they're birefringent. So what it does, like when it is unstressed, then the say X and Y, the refractive index corresponding to this direction and this direction are identical. So if you launch a plane polarized light, it will be plane polarized light. If you launch a circularly polarized light, it will be circularly polarized light. But with a strain, you can modify the refractive index of this direction or this direction. Okay. So now you have stressed the material in such a way that there will be a phase difference of say 45° between these two polarizations. So now if you shine a circularly polarized light, now the output will not be circular but a linear polarization. So in that way, if you model the stress periodically, then you will get a periodically the output light will be the polarization of the output light will be periodically varied. So you'll have a linear polarization, then a elliptical polarization, then a circular, right circular, then elliptical, then linear, then left circular, like this. So the polarization of the light is actually modulated, not the intensity. So it's a constant intensity, but the polarization of the light is changing with time. So then it passes through a beam splitter. It's a 50-50 beam splitter because in the return part I will explain why we need that. So there is a 50-50 beam splitter, and this is a movable beam splitter. So at the time of experiment, it's not there. I will explain why it is there. Then right now we just neglect this movable one. So the light is going like this and it's going down. So there is a objective, 10x objective, and then the sample, and these two are basically the magnet pole piece. So from the side view, if you see, the light is coming here, and there is a mirror at 45°, and the actual sample is loaded here because I want my magnetic field to be perpendicular to the sample. So that's why I place the sample like this, and light is actually going here and coming back like this. So and then at the return part, this is the return path. So now the beam splitter will reflect. So it will go to this path. Some part of it will go to this path, and there is an analyzer at 90°, and then the detector. So to get this reflected light in my detector, I have to put a beam splitter here. Okay. Now this movable beam splitter, because our samples are very tiny. My sample is though not much tiny, but it is order of micron level. So for my sample is like maybe 100, 200 micron, but we deal with samples with few microns, 2-3 microns. So we have to see where the sample is very precisely and put our spot exactly on the sample. So that's why we need a camera arrangement. Okay, so this movable beam splitter is just to see the sample. At the time of experiment, it's removed. So there is a camera, and there is another beam splitter. There is a lamp. So white light is going here, going in this path, coming back, going to camera. So in that way, we see the sample, and simultaneously this spot we see simultaneously on the sample, and we decide on which spot will perform our experiment. Okay, so this experiment is done with a liquid nitrogen cryostat, and this cryostat is actually made in our lab. So it can hold not nitrogen temperature. So I measured all this at 92 Kelvin. So at 92 Kelvin, it holds for 2.5 hours maybe. And it's a very quiet system. There is no vibration and all. So this is the thing we have made. So now with this setup, I try to measure the Magneto optical Kerr effect on MOS2, and this is the first curve. Yeah.
Small question. So in your sample, so you also need to put some reference, right? Like some to fix the Fermi energy, some electrical grounding, or just flake is just floating on top of the substrate.
This one.
Let's say when you shine the light on it, the sample is just on top of a substrate, or it has some reference, electrical reference.
No. So
the
silicon dioxide, SiO2 on Si, the substrate you also use. So on top of that, I have placed my sample. So and then I find under the camera where my sample is, and some good spot I put my light and measure the reflectivity.
Okay.
No, so Joylib is asking something different. Can I?
Yeah, right. I thought gating is some.
Yeah. So let's say this is your.
Why do you need gating?
No, not gating. So what people, other people sometimes do. So let's say the inner one is your flake. They have a separate, just one electrode to like put some voltage here, or let's say V is equal to 0, just to fix the voltage to something, and then excite with light.
No, why I would need voltage?
No, you may not.
So that will fix the Fermi.
Yeah, that will.
Yeah. So in our case, it's not. In our case, it's not needed. I mean, we do measurement like there are measurements called electroreflectance, where we apply electric field and then measure the reflectivity. There we have the similar kind of electrodes what you are thinking. So through that we apply electric field and modulate that electric field to measure. But in this case, so what I want to study is like under magnetic field how the reflectivity and the states are changing. So that's why you don't need electrical connection on this.
Okay.
The Fermi energy is not changing when you're shining the light.
Yeah.
You can do it. If you want to do another, you want another freedom where you want to change the Fermi energy and then see. But
yeah, exactly. Yeah. You can do that. I mean, obviously.
Yeah. Normally, most of these samples are unintentionally doped. So they have some doping in conduction band mostly, and type doping in many of these samples. So the Fermi level is either very close to conduction band or it's inside the conduction band. But we don't care about that normally when we are studying these samples just for doing Kerr effect, because you can still get some excitons as soon as you produce holes, meaning as soon as you shine some levels, some photons.
Okay, yeah, that's helpful.
Okay, thank you. Yeah. Helpful.
Okay. So with this setup at 92 Kelvin at 1.53 Tesla, this was my attempt to measure move parameters, and this is what I got. And now you will see that you see some signature, but you cannot definitely say this is whether it is a deep or it's a peak or a mixture of that, symmetric, asymmetric, and it's mixed. I mean, there is some signature, but it's not at all clear. So then we studied like where the problem is. So there are some problems. One thing is this objective, though I mean it is giving me higher resolution, I can perform the measurement on a very small area, but I am dealing with a bulk sample where if you can make a very good bulk sample, there will be like 200-300 micron clean area where you can there will be no scattering or anything. It's a plain area, but my objective is giving me say 10 micron spot maybe, but I don't want that. But it's actually cutting so much light because it has a very small opening, and several things are there. So actually light level goes down as soon as you use objective. So this is one thing I pointed out. And so if we don't need high resolution, why are you using objective? And the other thing is this 50 beam splitter that I have to put because I want to extract out my reflected light from the input light that I have to use. And that is actually cutting my signal by 1/4, because when it's going it's half, when coming back it's another half. So cutting my signal by 1/4. And the other thing is this liquid nitrogen, because I'm going till 92 Kelvin, and also my experiment time is fixed to 2 hours. After that I cannot do anything, and I can restart. I mean, I again start to vacuum, but it will take another 3-4 hours to restart the experiment. So these are the things we pointed out the problem, and then we rebuild the setup. So this is the new MOOC setup, where we're not using objective but using normal small lens. And the setup is, the other parts are I mean, similar to what we had. So this is the monochromators. There's the light it's going in the monochromators, the monochromatic light coming out. Then there's a adjustable mirror just to guide this angle. Then is a polarizer, then SEM PEM. Then again, this is a flippable beam splitter to direct this white light on the sample to see the sample. And then there is the input lens. It's going here, coming here, going back in this way. So someone was asking, Rishabh was asking probably, so what is the angle? So the previous experiment, that was 0 degree because the objective was exactly on top of the sample. But here we're coming at a very small angle, not exactly 0, but very small angle. So this is my input beam, this is my output beam. This is the direction of the magnetic field, the same kind of arrangement we have used. But here the cryostat is changed. Cryostat is not a liquid nitrogen cryostat, but it's a modified closed cycle helium cryostat. So with that, in this system, we can go to 32 Kelvin temperature. And then again, it is this Filpy-Well mirror for this camera, and then the analyzer, the lens, then the photo PMT detector, and this through to the measuring instrument. So you see this is the kind of spot. So this is my sample actually. So this is a very clean surface of a bulk MOS2, and this is my spot on top of that. So with that, I measured the same thing again, and this is the thing what I have got. Okay, these are supposed to be A, not delta, but I don't know why I'm seeing delta here. Okay, so now you can say the one thing is that the field has gone up. So now I can apply 1.86 Tesla, and this temperature is not mentioned. It's just 32 Kelvin actually. So this is 32 Kelvin. The temperature is lowered from 92 to 32. The magnetic field has increased, and now I see kind of two distinct things. Okay, these two things. So there is a definite dip and as a peak, and there is a curve like this overlap of, riding on this curve. Okay, so I see two distinct things, and there are two transitions. One is corresponding to A exciton, and the other thing is we are now calling it A star. We don't know what it is, but the thing is, it's obviously better than the previous one, but we can always improve our setup. So then there is no way to improve our setup anymore, but in the other part, like acquisition and all these things, you can still improve. So what improvements can we do? We can increase
Hello?
the yeah.
Can I ask a question? So
yeah, sure.
I was thinking this can this happen ki this result which you got is because of the lower temperature or the change in the angle of incidence or something?
Angle of incidence would not be.
But
because
what is the order of angle in the new setup? If you have an idea.
Yeah, so it's like order of 5 degrees, like 5-6 degrees.
Okay.
Like that. So there should not be. It will affect it, but there would not be drastically different signals for the 5 degrees.
And the temperature. The temperature is now.
Yeah, temperature is a significant thing. Yeah. So at 92 Kelvin, so basically what you are doing, you're trying to make. So there is okay. Let's go.
So maybe so have you taken any measurement? So here it is what temperature?
There is 32 Kelvin. I have not mentioned.
32 Kelvin.
This is 32 Kelvin.
So this is 32 Kelvin. So maybe we can take measurement on the maybe 72 kelvins with the measurement that as we have taken the previous graph.
Yeah.
So that will clear ki these
So no, I'm saying you is definitely temperature effect. So that's I want to emphasize here that what you are doing actually. So there is something like this, some transitions. Okay. So this is corresponding to say E naught. Now what you are trying to measure, so you have applied magnetic field, and now this energy, this structure has shifted. Okay. So now you are trying to measure this delta E, right? So now how efficiently you can measure this delta E depends on the sharpness of this, right? And this sharpness is proportional to the gamma factor, and gamma factor goes down with temperature. So with in lower temperature, this feature will be even sharper, and you will efficiently measure very small shifts here. So in the previous case, when it was 92 Kelvin, the structure was so broad, say like this, and even if there is a very small change, so these energy changes are order of micro electron volt. So you are measuring in electron volt, and you are trying to measure a delta E which is 10 to the power 6 order less than that. So effectively, you will not get any difference. So these curves are basically the difference of these two spectrums. Okay. So the difference will be very, very small, but you cannot measure that. The difference is there, but due to the temperature, it is so broad, but you cannot measure that. So that's why as soon as we went from 92 to 32, we start to see some signal.
Okay.
And also we have increased the light throughput through the the input light intensity was less through when it was through objective. Now we are using a lens, so light throughput has gone up. So my signal will go up.
Okay. And what is now the spot size of your excitation?
So I show you now.
Wavelength?
So that is I showed you here. So
it is okay, around 100 microns.
No, 200 cross 250 micron or something like that.
Okay, that's it. Okay, thank you so much.
Okay, so what improvements we could do? Yeah.
So then this is your resolution, special resolution, or you can do better?
No. In this setup, I cannot do better.
Okay.
That is my special resolution. Okay. So what improvements we can do? We can do time averaging. So the signal to noise ratio will improve. So my measurement will take longer time, but will get cleaner spectrum. The other thing can be the how the way you are actually doing the data acquisition. So previously we used to do using through so it's all lock-in measurement. So you write LabVIEW code and you decide how we will do the data acquisition. So we are using some code which was actually taking one data at a time and then doing the averaging. But then we change our data acquisition technique to something else where we continuously for say 10 seconds you are averaging. So continuously it will take 10 second ka data and then it will do averaging. So we have seen that it actually makes significant difference depending on how you are actually doing the data acquisition. So we changed that in our data acquisition program. And then one thing is that you measure it. So we have to do several measurements in several magnetic fields. So there is always some kind of drift which is you cannot control. I mean, due to temperature slightly varied, there will be a slightly defocus, and all these things will happen, which you cannot control at all. So there will be a kind of drift, but you can cancel the drift if you do simultaneous measurement at different fields. So what previously I was doing, let's say at 1 Tesla, I do the whole measurement. Then again, I start from 2 Tesla, I do the same measurement. So the background of these two measurements are different. So now, so finally what I did, so now this is at say 1.9 TeV, I measure 0 Tesla, 1 Tesla, 2 Tesla. Then I go to 1.91 EV, I do 3 simultaneous measurements. So like that, you can actually, it's not ideal, but from the previous, what we were doing previously, and compared to that, it is a better way to suppress the drift. And also we changed the something called I2V converter, which is basically we are using PMT, right? Photomultiplier tube that actually give rise to current, but lock-in cannot measure current. You have to transfer that to convert that to voltage. So there is something called I2V, current to voltage converter. But every instrument has some limitations. So the frequency we are working with is at 42 kilohertz. And for mock measurement, you have to do two measurements. One is 42 kilohertz and there is 84 kilohertz. So in that range, usually, so in our lab usually do measurement at 170 hertz, 220 hertz. So our devices are, based in that region. But as soon as you go to 42 kilohertz and 84 kilohertz, the device response actually goes drastically down. And actually in that, like other I2V, the company actually doesn't mention anything about their, I2V converter in that frequency range. But thankfully we had another current to voltage converter, which actually built to work in the higher frequency regime. So we replaced that I2V with the new one. And
so which I2V was this company?
This is DHCPA or something.
I understand what you mean.
It's a smaller rectangular. Yeah. So then we
Femto systems.
Femto, yeah.
These transport guys would know it better, right?
Okay.
And
then
small thing, sorry. So why do you require that frequency? Like you can do go to
because
lower...
I'm limited by PM. PM is actually a device. So there's a few silica bar, okay, and you want to press that. So it's a huge fused silica bar, and you have to press that in closer to the resonance of that bar. So what company sells this PM, it has some specific frequency. Only at that frequency it will modulate the polarization. So I'm bound by that. As I'm using PM, I have to work with 42 kilohertz, and I have to measure second harmonics of that.
Okay.
If it is a normal case like chopper, I can go down, but here I'm bound to that. It's a very precise 42.9 kilohertz. Yeah, then if there are so room for improvement, we did what Nike suggests. Anyone? What Nike suggests? What they tell us is for fun. Okay, so they say just do it. So we did all these changes and measured the spectrum again. And this is the latest version of the data. That was the second curve. I have told you the story from transformation from that curve to this curve. So here you see the temperature is 35 Kelvin. I can go till, actually I can, in this setup, I can go even more, but then the heating and this thing come to play. So I measure till 1.9 Tesla. I can go to 2.2 Tesla now. So this is at 1.9 Tesla at different field. And this is the simulation of that curve. So it matches very well. The signal to noise ratio is very good. And we can definitely say there is a dip, and correspondingly there is a peak. And there is a structure like this and another structure like this. Okay. But what I wanted to emphasize is that you see finally just one curve, but something, all these curves, I've just shown you few, there are even more. And all one, like two of these curves is one sleepless night. And eventually you'll get something very good, but you have to measure all this bad spectrum to get one good spectrum. And now I want you to so here you say what is the significance of all this junk data, what it seems like, but here you see the significance. So now I have measured on so many samples now, on so many magnetic field and so many times, I have a distribution now. So all these points are actually one sleepless night, but now they're giving me, I mean, like this curve when I fit, more data points are there, you get better estimates. So for now, I have a very good estimate for this G factor of A exciton, and this one I will explain. Okay, so not all, initially it seems like everything is going in vain, nothing is happening, but eventually this inset cost you several sleepless nights, but it means something. Yeah, that
Dibya?
I wanted to say. Yeah.
Yeah, these curves look quite impressive. The signal to noise ratio looks quite good. How much is the minimum angle you can, or how much is the signal to noise ratio here in terms of angles? Do you know?
Okay, so the minimum, so this is at 1.2 Tesla, but if you see somewhere, let me see here probably, so these are at 0.5 Tesla. So even there, like
No, just what's the noise level? Is it 0.001 degree or better?
Obviously 0.001 degree, order of that, 0.001 degree. Yeah.
Okay, because it
In
looks like
all our measurement is like that. Yeah.
okay.
Okay, so then I again go back to PhD comics and say, like, as soon as I say after 3 years with so much effort, I have prepared one curve, maybe that will be just figure 1 of your thesis, or maybe not figure 1 but figure 1A, but it's fun to do and it's worth to do. Okay, so what is the
Dibya, one more thing. So for taking one set of spectra, which you take at different magnetic fields, how long one spectrum takes for you?
I knew I will ask this, but yeah, it takes a long time. So the final thing, what I did was like everything will be taken in one shot.
Yeah.
So I'm changing the monochromatal light and in 3 different magnetic field, including 0. So basically 4 different measurement at 1 energy, and then it continues.
Yeah.
So that total measurement used to take me around 4 hours, 5 hours, like that.
I see. So this spectrum set which you showed on previous slide took like 4 to 5 hours, something like that.
No, so before that I used to do individually. So if you say me this red curve,
yes,
red curve, this eta and phi red curve will take me about 1 hour to measure. But now I do simultaneous measurement in 4 different fields. So that's why it takes 4 and 4.
And how many data points do you have in one spectrum?
So it is taken at 0.5 nanometers.
So what's the wavelength range? I can't, because this is energy.
Okay, so I used to take from 610 to 670. So 60 data point, 0.5, matlab 120 data points.
120 data points, 1 hour. So that means you take half a minute for each data point.
Yeah, half a minute everything for that.
Okay, thank you.
Okay, so now I come to what is the physics behind that, and all these peaks and dips are corresponding to. So this is the reflectivity spectrum corresponding to this MOS2. This is the reflectivity spectrum, and what Shuaida was asking. So this is corresponding to the A exciton, and so this is the usual exciton what we are talking now. But for this material, there is something different. It's called B exciton. I'm not going to that, but there is another way you can form exciton in this material. So that's why they're called B exciton. These are 2 prominent exciton transitions. But there is something, hump kind of thing is there. But the question is, what is that? So for a long time, people have predicted it differently. Someone told this is actually n equal to 2 transition of the A exciton. So there are exciton levels, and the amplitude of the level actually goes down just like hydrogen atom. So n equal to 2 will be shifted to energy, but the amplitude will go down. So it's good guess to guess that this is a n equal to 2 transition. Then from our lab only, I think Nihit is also, I saw him here. So Nihit wanted to say this as H point transition, some other explanation, because it was not matching with, if you assume that that is n equal to 2 exciton, then the energy and binding energy, all this thing, it doesn't match. So that's why he predicted, suggested that this is something called H point transition in this material. But so we have measured the smoke in this part only. So here you see there's a change of phase. So for this one, you're measuring it as a dip, but here it is a peak. So now this represents G factor. Okay, indirectly it did represent G factor. So the G factor corresponding to these two structures are different. Drastically different. Why? Because here the structure is very strong, and corresponding to that you are getting this signal. But here the structure is very small. Here, this is very large. I wanted to say. So this is very large, but here getting this signal. But here structure is very small, but you are getting almost comparable signal. It means the energy shift is much more in this case rather than this case. So G factor of this state is much more than the A exciton transition. So here you see, this is the G factor. From that slope, you can actually go on the G factor. So the G factor corresponding to this transition is minus 2.9. And for this is actually opposite, and not the sign is opposite, not only opposite, the value is very large. Okay, so it is plus 11.4. So then this cannot be n equal to 2 or H point transition even. Okay, and so then what it is? So Ashish is there. So Ashish wrote a paper in 2017, and he showed that in material something like this, MOTE2, in that material, he showed that this is something called interlayer exciton. And what is that? So we told that this is a bound system in one layer. Okay, so the electron is here, hole is here, everything is bound in this one layer. But there might be one possibility where this electron is in this layer, but the corresponding whole of that exciton is in the other layer. Okay, so in that case, they did some calculation and showed for this MOTE2 case, the G factor should be actually opposite. And though not for their case, it was not the large like this. It was not 11 or something. But the concept came from here that if it is a positive G factor, it is probably to be interlayer exciton. So now we say this is the intralayer exciton, A exciton, and this is corresponding interlayer A exciton in case of MOS2. So I'll explain why the sign is opposite, how we wanted to, what Ashish gave the explanation. So in intralayer exciton, this is actually this is the lowest of the conduction band, this is the highest of the valence band. So these two are the levels which actually forming the interlayer exciton. This is at B equal to 0, and what is the interlayer exciton is forming in this layer, in this state. Okay, so you see this is upspin, and this is downspin. So the intralayer exciton is formed by two downspin states, but interlayer exciton is formed by two upspin states. So as soon as you apply magnetic field, this will go down, this will go down, this will go down, but this will go up. So this now have opposite direction of movement. So this has increased, but this has decreased. So from that way, you can explain why the sign would be opposite. For this case, this is negative. For this case, this is positive. But the question still remains why the value of that is so large. The 11 plus 11, and till now, as far as I understood, we still don't know why for MOS2 this value is plus 11. So we understand the sign should be opposite, but why this is plus 11, we don't know it. So, well, yeah, thank you for your attention, or at least pretending that you are interested. And I'm leaving you with these two representative things, the crux of this talk actually. And if you have any question, you can ask. Otherwise,
I have a question.
Okay.
So you have taken reflection measurement So
Hmm.
and also in that graph we can see there is around less than 50% reflection. So after absorption there will be also some transmission. Is there some transmission in your sample?
No, it's a bulk sample. Uh, so there's something called that optical depth or something. Yeah.
So what is thickness of your sample?
The thickness is I've not measured, but it is obviously in the microns. I mean.
Okay, so
maybe
there will be no
100
transmissions.
No. Yeah.
Okay.
Below the band gap, there will be transmission. That's why you were seeing interference.
Yeah.
What I was thinking is कि maybe we can see some feature in transmission also, and taking transmission is I think little easier than taking reflection.
So there's another kind of measurement. It's called Faraday rotation measurement. So here you are trying to measure how much polarization has changed due to reflection. But the same measurement you can do in the transmission mode also. Like it's a very thin sample, and you launch a polarized light, and in this side you measure how much that polarization has changed. So people also do that also. This is called Faraday rotation measurement. It's similar to MOC, but that is in transmission mode.
Okay. Thank you so much. बहुत ज़्यादा मजा आया आपकी स्लाइड देख के. So thank you so much.
Yeah.
Dibya,
Yeah.
so this G factor of +11 which you are getting, in some recent papers in the last 3-4 years, people are getting +8 from their reflectance, Magneto reflectance measurements. Have you checked those papers by any chance?
Which paper? So I came across one paper where, but their logic was not, profound or
yeah, I mean, about why it is so is of course questionable, but the numbers, I mean, the numbers are.
Yeah, the 8, the paper they predict 8. I have gone through that. But their data quality is very, very. I mean, even they say that for interlayer we estimate it like that. The signal to noise ratio is so bad that we cannot.
No, that is true. But on the other hand, very recently, just last year, I published with better data quality, and there I also get.
Okay.
You can take a look on this paper, which was essentially a review article. This was a perspective article in Journal of
Yeah.
Where I have published this data.
Okay, I will look into it.
Anyway, sorry, but that was a bilayer. In bulk also I got 8 actually, which I did not publish. I can share that data with you at some point.
Okay, sure. Yeah.
Okay.
Thanks, Dibya, for the nice talk. So one small question. So this small hump you are saying is interlayer. So have people done like monolayer studies and have not observed that feature?
Yeah. Vishwas has done this. I mean, not more, but in other kind of measurement, PR, photoreflectance, electroreflectance. He has studies actually layer dependent of this spectrum. So in a monolayer, you see only A exciton and B exciton, nothing in between. But as soon as there is bilayer, you see a strong interlayer response there.
Okay.
And nowadays, I think I came across some article that they vary the spacing between that. I don't know. So putting HBN in between and then creating a slope, this kind of, when they try to measure from the HBN how this interlayer strength is going down and this kind of measurement.
Okay, and they really find that with distance it goes down.
No, with distance actually go up because here it is closer. So interlayer will have more strength here. And as soon as you put a wedge here, so here it will be like this. So interlayer coupling has gone down. So here you will see less interlayer, and here you go more interlayer.
Yes, means as distance increases, it will go down.
Yeah. Yeah. If not anything, then I'll stop sharing.
Thank you for that. This talk is quite wonderful. I mean, we have learned a lot of things from this talk.
Thanks. Yeah.